Hello, this is my lab report for Lab 2. So the purpose of this lab was to drop a ball from rest and have it go down in a straight line, and then use the tracker software to analyze the video and find the position versus time of the moving object, and then using Newton's second law to create two models that predict the position versus time. One would have just gravity force and one would have gravity and drag force incorporated. So here is my video in tracker. So it's just a crumbled up piece of paper going straight down. And then here is what my data is like. So in order to make the two models, I'm using the Newton's second law, or the momentum principle, which helps me find the position update formula and the velocity update formula, same as Lab 1. And then I'm also going to be using gravitational force, which is negative mass times the gravitational constant, 9.81 meters per second squared in the y direction. And then there's the drag force, which is the b constant times the magnitude of velocity squared. And the b is positive because it needs to be the opposite sign of the velocity, which is negative. And then adding those two forces together gets the net force. And then here are some data points that I used. The mass of the ball, the time of the first observation is at 0 seconds, and the last one is 0.5 seconds. Delta t is 0.033 seconds. When they're in the model with no drag, b is just going to be 0 because there's only gravity. And then in the one with drag, the b will be 0.006, which I found using trial and error. And then there's also the arrow scale, which I use the length of the weight arrow, which I decided to be 2 meters, divided by the mass and the gravitational constant to get 45. And so here is my code for the model without drag. I have the mass of the ball, the starting position vector, the starting velocity vector, which it starts at a velocity of 0 because it's at rest. And then I have j hat as 0, 1, 0 because we're only looking at the y. B is 0 because the model is only gravity. And then I have the weight force, which is negative mass times gravitational constant, and that's going to be all that we use for the net force. So this is what it looks like when the program runs. You can see that the model is pretty similar to the tracker model. And then with the drag force, I have b as 0.0006, and then I have the drag force formula as b times the magnitude of velocity squared. And then I have the arrow that represents the force, the drag force, and the gravitational force. And this is what it looks like. So here it is graphed. We can see that the both of the models are accurate at the beginning to the experimental data, and then towards the end it goes off a little bit with the model without drag, especially because it predicts the object falls farther than it actually does, because it doesn't take into account the air resistance or the drag force. And so I have the model with the drag force, and it's more accurate. There is a little discrepancy here at the end, which could be a number of reasons, such as the video not being perfectly straight and just human error with the way that I tracked the video. And so can we tell the terminal velocity from the models? So terminal velocity is when the net force is 0, so the drag force and the gravitational force would cancel out, and we would have velocity would be constant. So we can see here that the velocity is not constant because the velocity is going down. It's not in a straight line, and neither with the other model. So we can't see the terminal velocity here, but we could predict it by seeing when it would start to start being more constant. And then if the ball was initially thrown instead of from rest, then the velocity would not be 0, it would have a starting velocity. So if I had a starting velocity, I chose a starting velocity of -7 meters per second, and in that case we can see that it is more concave down than the other ones, which means that the terminal velocity wouldn't change, but it would get there in less time. Thank you.